Okay, so this is a related rates question, right? We are talking about certain rates here, 3 revs per minute. And it's asking, then the question itself is asking how fast is the light ray moving? So we definitely want to talk about related rates. Okay, so a diagram is given to make sure that you kind of understand what's going on, but I wanted to add more information to this diagram. And we also know for related rates, I then want to extract the information from the English words of the problem. I want to write relations between my variables, right? There's a few things that are going on here. So actually make this quite a large line there. So let's make that a little bit shorter. Okay. All right, so what are the variables in this problem, right? And is that variable constant or is it changing over time? What do we think here? Who wants to volunteer some stuff? How should we label this diagram? May have stumped some people. Let's actually look at the problem then, the statement. Let's first focus on the 3 revs per minute. That is a certain rate of change, right? Something is changing at a rate of 3 revolutions per minute, right? What is changing at a rate of 3 revolutions per minute? What? And we want to answer, first ask yourself, if you're not sure exactly what the answer is, first ask, what type of variable is changing at 3 revs per minute? Is it a length? Is it an area? Is it an angle? Is it a volume? Is it something else entirely, right? What type of variable is changing at a rate of 3 revolutions per minute? But don't tell me the lighthouse, because lighthouses don't change at revs per minute. Num says the angle. Jonathan, the angle of the light beam. Good. So the angle here, so this angle theta, that is the thing that is changing at 3 revs per minute. So as we label the diagram, we can also put in our information and relations between variables. So can someone already tell us some piece of information here with regards to theta? How would I write the equation? The lighthouse rotates anti-clockwise at 3 revs per minute. What equation would that be? D theta dt equals 3. Okay, so there is a very slight mistake with this, but it's okay because I actually have never talked about this, which is why I'm doing this. So someone said -3. Okay, well the answer is it's not negative, so positive was correct. So remember, if this is rotating anti-clockwise, that means this angle will actually be increasing over time. So the fact that it's positive does, the fact that it's increasing angle, it is a positive rate of change. Remember, if it were going clockwise instead, that means the angle would actually be decreasing. So the positive is correct. It turns out that the number is incorrect. So it's not 3. Now this is the reason for this is because I gave you the units in revs per minute, revolutions. But this is a subtlety. Whenever we do anything with trigonometry, everything has to be in radians, right? The reason is, one of the most important reasons, if you're not working with radians, remember that the derivative of sine theta is cosine theta, right? And derivative of cosine is negative sine theta and so on. All those derivative rules for trigonometric functions, they don't work unless the angle is measured in radians. So all angles in all of these problems and all of calculus must always be measured in angles, or measured in radians. So what number should I put here? So 3 revs per minute is equivalent to how many radians per minute? The angle has to be measured in radians. How many radians is that? 3 revolutions is how many radians? The 1 revolution is 1 all the way around once. So 3 times around is how many radians? Well, 540 would be degrees, and 540 would actually be what? 360 plus 180. So 540 would actually be once and then half. That would actually only be 1.5. So 360 times 3, again, that's degrees. I need radians. 6 pi, good. put a little note here. Angles must be in radians. We're not using 3 revs per minute. I mean, we are, but we're just writing it in terms of radians per minute. Okay, so we've taken care of one of the variables theta, and we've already gotten some of the information. So if I go back to the original statement of the problem, we've actually already taken care of quite a lot of this, right? The lighthouse is 2 kilometers away. We've taken care of that. That's in the diagram. The lighthouse rotates at 3 revs per minute. That's already taken care of. Now we need to focus on the last sentence. How can I translate this sentence into English? Let's look at the first part of it. How fast is the light ray moving along the shore? Right? And let's stop there because the next part of the sentence starts with when blah 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 blah. So obviously that's another piece of information. So this part that's highlighted just tells us what are we looking for. We're looking for how fast the light ray is moving. So in other words, I need a variable whose rate of change would be the answer to how fast is the light ray moving. We have not yet introduced a variable that kind of corresponds to that. So what variable should I label in my diagram that can eventually let me answer this question of how fast is the light ray moving along the shore? Now, if you tell me x doesn't tell me anything. I need x. You tell me what does x mean? Is x, what type of length is x? Right, x would be the distance from what to what?
The light ray to the shore?
Okay, the light ray to the shore. But what do you mean the light ray to the shore? Because the light ray is already on the shore. Or this whole thing is the light ray.
The distance from the source of the light ray to the shore.
Well, the source of the light ray is the lighthouse, and
Yeah,
the distance to the shore is 2 kilometers. That's a constant. Do you mean along the light ray, not the
along
okay.
the light.
So the distance from the lighthouse to the shore, but along the light ray. So let's call that, in my notes, I actually called that D. Now let's ask, if the answer to the question, how fast is the light ray moving along the shore? Would that be d dt, dd dt?
It would be the distance from where the light source hits the shore and p.
Okay, good. So actually, the rate of change, we are going to need this length, so I'm going to leave it there. But the length from the lighthouse to this point, let's actually label that point. Let's call it let's actually call it Q. So the distance from the lighthouse to Q is important. However, to answer the question, how fast is the light ray moving along the shore? I actually need to know the distance from Q to P. And we can call that, say, Y. And in fact, let's change the D to L, just so I don't just keep saying like D, 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 D. So many Ds. Right, so the moving along the shore actually indicates that I want to know something about how this point Q moves up and down the shoreline. So I actually want to know what is dy dt. So the rate of change of that distance y is in fact how fast the point Q is moving along the shore. And then the last part of the question said, get rid of some of this. The last part of the question statement says, when it passes by a point on the shore that is 4 kilometers away from the lighthouse. So this describes to us, we're used to this by now, it describes to you the time that you're actually interested in, right? That snapshot time. How can I describe that snapshot time in terms of the variables that I have defined? So I should write here, I want to know dy dt when what is true. So when the point passes by.
Is it when L equals 4 kilometers?
That's correct. When L equals 4 kilometers. So when the point Q is 4 kilometers away from the lighthouse, in other words, when L equals 4. So that's why you can see we actually do need L in this. Okay, so the relations, I'm not going to have enough room in that column, so I'll write the relations now down below. Okay, so now we've gotten everything we can from this question, right? Everything is kind of extracted. So now let's start writing equations that relate our variables. Jonathan, your mic is a little hot. Okay, so what are the equations between my variables? So I have L, theta, and Y. So let's come up with some equations between these variables. Sine. Well, that's not an equation. That's just sine. Or sin. Maybe you're telling me I'm doing a bad job. Cosine of theta equals 2 over L. Okay. There's a lot of stuff we can actually write here. We can write cosine of theta equals 2 over L. Kasim and Victoria both said something about sine. So sine theta equals opposite over adjacent. So I can say, sorry, opposite over hypotenuse. So I can say sine theta equals Y over L. So that is an equation that kind of involves all of the variables at once. One of the issues here is, which relation do you actually want to choose? Now, notice that I am actually not given anything about dl dt. Technically, I can get dl dt from the rest of the problem, right? Because there is a relationship between L and the other variables. But because I kind of I would like to avoid L as much as possible, only because I don't know dl dt directly. So although cosine theta and sine theta are both correct, I'm actually going to use tangent theta because tangent theta involves y and this constant 2. So tangent theta, that would only involve the y variable, and I already know that's kind of what I want to know anyway, right? I want to know dy dt. So again, if you decided to use cosine or sine, you can still solve the problem. I think the algebra will just end up being a little bit more difficult. That's all. So I'm going to write down tangent theta equals y over 2. So 2 tangent theta equals y. Okay. Now, given that I have this equation, how I'm solving the problem, I do need another equation because my equation so far does not even involve L at all. It's actually going to turn out I really don't need to have an equation with L, although I am just going to write it. So we're going to use Pythagorean theorem there. Y squared plus 4 equals L squared. But it turns out we're really actually not going to even need that equation. Although it's not clear yet why we won't need it. Okay, so now what do we do with these relations? We differentiate them. Right, so 3 will be the derivative of 1, and 4 will be the derivative of 2. So I'll give equation 4. So the derivative of equation 2 gives me 2y dy dt equals 2l dl dt. Who would like to give us equation 3, which is the derivative of equation 1? Like Noam is typing something. Let's see what we said. So 2 secant squared theta, good, times d theta dt, good, equals dy dt. Very good. Okay, so now we have all of our relations. All right, so right now the whole problem has been set up, right? This is kind of the first major step of related rates, right? This is kind of the modeling part, right? I've given you an English statement, and now you've translated everything. I had my diagram, I've translated the information, I've translated the relations. So any questions about the problem so far? Okay. All right, so now we're on to the second part of this problem where we actually substitute and solve. Right? It looks like some people are typing, probably a question. So I'm going to start writing, and then once you type, I'll answer your question. Okay, so now substitute information and solve for dy dt. Right, because that's eventually what I wanted to solve. Recall that we wanted to know what dy dt was. Okay, so these four equations, 1, 2, 3, 4, they will now become new equations that hold only at the snapshot time. 1 star, 2 star, 3 star, and 4 star. So I can't have everything on the screen at the same time. Let's kind of just remind ourselves, what is the information we're substituting? We're substituting in d theta dt equals 6 pi, and we're substituting in L equals 4. We would like to know dy dt. So equation 1 gives us 2 tan theta equals y. It literally gives us nothing, that first equation. Right? We don't know theta and we don't know y. The second equation gives us y squared plus 4 equals 4 squared, so 16. 3, if I substitute in, so d theta dt is 6 pi. So here I would get 12 pi secant squared theta equals dy dt. And then the last equation, I get 2y dy dt equals 8 dl dt. Remember, convert L is 4. Okay, so now we have a set of 4 equations we need to solve. But keep in mind, we don't need to solve for everything, right? This is, even though this is a simultaneous set of equations, I don't need to find every single variable, right? The only thing that I'm actually interested in, right? First of all, what are the unknowns, just to make that clear? There's theta, there's y, there's dy dt, there's dl dt, right? We have 4 unknowns with 4 equations. So in principle, we could solve for all 4 of them, but I don't need all 4 of them. I really only care about getting dy dt. That's the only thing I really want. The other stuff, if I need to get them, I'll get them. But if I don't need to get them, I don't really care. In particular, we're actually not going to solve for theta directly, and we're not going to solve for dl dt directly. We will be getting y, though. Now, in principle, the only thing, if I'm looking at just this equation, this is the only equation that involves dy dt. In principle, if I knew the value of secant theta, I don't even need to know the value of theta. I just need to know the value of secant theta. If I knew the value of secant theta, this equation is then solved and I'm done. So in fact, it turns out that's the easiest way to do this. Instead of trying to solve everything, kind of shuffle around the equations, let's just get secant theta. So for that, I'm going to draw a diagram. So at the snapshot time, we have the following diagram. Draw the triangle. That's supposed to be a right triangle, but whatever. All right, so here's theta. This distance was 2. This distance was 4. And this distance is y. I don't even need to know what y is. All I really need to know is, so this is the diagram of that snapshot time. I only need to know, can I already get secant theta? Do I even need to know the value of y? No, I don't. Because what is the secant of theta? Secant of theta, recall, is hypotenuse over adjacent. All right, remember, why is that true? Because cosine is adjacent over hypotenuse, and secant is the reciprocal of cosine. So secant theta gives me hypotenuse over adjacent, which is 4 over 2, which is 2. So in fact, I can get secant of theta directly without ever needing to solve any other equation. I don't need to solve for y. I don't need to solve for dl dt. I don't need to solve for theta directly, right? I have secant theta directly from this diagram. So that's really nice because now I can just go right back to equation 3 star, which is at the top of the screen. Going back to 3 star and putting secant theta equals 2, we get 12 pi times secant squared, which is 2 squared, equals dy dt. On the other side. We get here, what, 12 times 4, so we get 48 pi. And what are the units of this? Y over, right, a dy over a dt, that means units of y over units of t, right? Length over time. The length in this problem was measured in kilometers, and the time was measured in minutes. So we get kilometers per minute. That's all. So notice that by being very judicious and drawing the diagram, this is very useful for these types of right triangle problems where you have to have an angle in it. It's very useful. You might end up getting a lot of equations like this in a right triangle problem that involves trigonometry and angles. But a lot of times you don't need to solve for all those equations at once. You can usually, a lot of times, just draw the triangle at that snapshot time and then read off whatever you need. You can read off secant theta, tangent theta. You can get whatever you want from that diagram. Now, as kind of another note, a lot of students at the beginning, when I first asked what are the relations between the variables, some students suggested things like cosine of theta equals 2 over L, sine theta equals y over L. So notice that those equations would have been a lot more work because when I differentiate cosine theta equals 2 over L, that equation is going to now involve the L dt. So if I want to get dy dt, now I need to know how to find dl dt. And so I would have to actually then solve this fourth equation. Notice how being judicious and trying to include as few variables as possible in each equation, right? I'm only including theta and y in this equation, not theta and L or theta all three at once. We actually cut down on a lot of work. Any questions about any part of this problem? Okay.
So when we see like theta, do you automatically go to like trigonometry?
Yes, I mean, yeah. So if a problem involves like a line of sight angle, other problems you've seen involving line of sight angles, sometimes, like we have like a man over here, or like a photograph or something, and some balloon is rising, in the air, and you want to know about the angle of his line of sight with the balloon, something like that. A lighthouse rotating. So these problems do appear naturally. So whenever you see something like that, a line of sight angle, yes, there's going to be a trigonometric relation because somehow that angle is going to be important. And so to get angles into this geometry, you're going to need some sort of trigonometric relationship. So yes.